Welcome to Math 335. I'm Professor Jensen, and I'm going to make these videos to kind of help with the instruction that would have gone on if we were able to meet in person. And so, with my colleagues, some years ago, we developed a supplementary note packet for this book, and we use it to kind of guide our lectures. And so, this would be something that I would have used in class. And so, what I'm going to do is just kind of talk and lecture the way that I would in class, and then do the problems right here on this screen so that you can see some things worked out and have reinforcement as you go into the homework and have some experience there. I can also post some videos with specific questions being answered from the homework, and so I'll kind of see what the homework looks like, create some videos that I feel are good, and then take feedback from you as to things that you need to see. And so as you look at your first module, it is just kind of making sure we have a strong foundation. And so everything's here in the guided notes, pages 3 through 12. So let me scroll down to there and start looking at that one. So here's page 3, and we want to make sure that you have some key functions known. So what you have a picture of on this left-hand side is the absolute value graph, right? So we want to make sure that you know that this is a V-shaped graph that has a center right here at the origin 0, 0. And then the way that we want to talk about these key functions is to make sure that you know what happens when we do certain things to them. And so as we look at this number 1a, we see that there's a negative sign right here along with the absolute value. So what that's going to do is take all of our previous values and turn them over. So ideally what we're doing is what's here first. We're sketching. We're not necessarily plugging in points. One thing that's going to really help us is quick analyzation of problems to see how are they affected by this and get a good picture right away. So hopefully from your previous experience, you know that this negative on the outside is going to take that V shape and flip it right upside down. So where we were passing through 0, 0, we're still passing through 0, 0. But we were passing through something like 1, 1. But now we're going to pass through 1, negative 1. And we're going to pass through negative 1, negative 1. And so forth and so on. And so we want this kind of quick picture of this. If you have a negative or a subtraction going on the inside, it definitely shifts your graph. This is happening before we take the absolute value, so it's going to be a change in our x. And if you're going to take x minus 3, it's going to either shift it to the left or to the right. But because it's minus 3, it's actually going to shift it 3 units over to the right, and it's still going to open up and be that exact same V shape. So what it's doing is it's taking this origin point and shifting it 3 units to the right. One way you can verify that is to plug in 3. If you plug in 3, you get y is equal to the absolute value of 3 minus 3, which is the absolute value 0, which puts you at that same y value 0. Now, if you take and subtract something after the fact or add something after the fact, what that's doing is it is dropping you or raising you. And so because the minus 2 is after the fact, we're actually going to take our regular V-shaped graph and drop it down to from its original 0, 0 position. And so we take this kind of key point right here, this origin point, and we shift it. We flip it if there's a negative on the outside, move it to the right if it's a minus on the inside, left if it's a plus on the inside. If it's a minus on the outside, it's down that many units. If it's a plus on the outside, it's up that many units. Apologize, I wasn't paying attention to the thing that was over here, the stuff that was over here on the left-hand side of the page. This, when it talks here, it's wanting us to identify the domain and range of this graph right here, this absolute value graph. So the domain is all reals, right, or negative infinity to infinity, and the range is from 0 to infinity. And so they want us to get a habit of identifying domain and range really quickly, or at least we do. So take a look at this one. Several things are happening. We are being moved in certain directions. This plus 4 means that we're going 4 units up. The minus 1 that's on the inside means we're moving 1 unit to the right. So our original vertex is going 1 unit to the right and 4 units up. And we got a dot right there. That's where our vertex is. Now typically we'd open up, but there's a negative on the outside, so we're actually going to be that same V shape but opening down, coming down right through there. Now if we plug in a 1, we can see that we would get a 4 out. If we plugged in a 2, we'd have 2 minus 1. Absolute value of that is 1 plus, but it's negative, right, because of the negative sign out there. So let me show you what I'm doing here. If I let x equal 3, or sorry, x equal 2, that will just check to make sure we're headed in the right direction. And so this is only a check. If you're comfortable with what all of that should have done, just walk away. But if you have a 2 in there, get absolute value 2 minus 1 plus 4, which is y is equal to negative the absolute value of 1 plus 4, which is y equals negative 1 plus 4, which is y equals 3. And that looks exactly right as we go through there. So it's doing exactly what we thought it would do. We also want to make sure we can evaluate some functions. So in number 2 it says evaluate and simplify each expression. So remember what f was. F of x. Let me fix that really quick. F of x is the absolute value of x. So what's f of 4? It's the absolute value of 4, just 4. What's f of negative 7? The absolute value of negative 7, or 7. Pretty simple. Determine the following statement is true or false. Show your work. So is f of negative 4 plus f of 3 really f of negative 4 plus 3? Let's check it out. So one way to tell is just to independently work the left-hand side and the right-hand side and see if they coincide. So let's see if this is true or false. So f of negative 4 is the absolute value of negative 4. F of 3 is the absolute value of 3. Is that equal to? We don't know. Is that equal to the absolute value of negative 4 plus 3? Well, absolute value of negative 4 is 4. Absolute value of 3 is 3. And so the total on that left-hand side is 7. The negative 4 plus 3 is negative 1. And the absolute value of negative 1 is 1. So no, it's a false statement. And that's all we're wanting to do there, is just make sure that we have the function notation handled correctly. As we look at this Roman numeral 3, it's reminding us that f of x is equal to the absolute value of x, and it wants us to find to solve when the absolute value of x is equal to 6. So we just have to ask ourselves, what do we take the absolute value of to get 6? Well, obviously that's 6, and then also negative 6 as well, both of those answers. What do we take the absolute value of to get negative 8? Well, the answer is nothing. There's no solution. The absolute value is a measurement of distance. It's how far you are away from 0. And negative 8's not a measurement of distance, that is to say. And so, therefore, there is no solution coming out of there. And then now we want to know when the absolute value of x minus 2 is equal to 5. Well, that's when x minus 2 is flat out equal to 5. That would cause it to be that way. But also if that x minus 2 could work out to be negative 5, it would also force that hand. And so we're just reminding you of an intermediate algebra concept of solving absolute value equations while we can, to come up with two unique solutions of 7 and negative 3. Both of those will work. As I go back up here and we look at Roman numeral 4, we want to write the function for each graph. So let's take a look. This is our regular absolute value function, and it's been shifted to the left 4 units. Well, what's that? That's f of x is equal to the absolute value of x plus 4. Because we know that. So we want to just get double reinforcement. This one right here is taking that regular absolute value of x graph and shifting it up 1 unit. And as we look at C, a few things have happened. Something that's happened is we flipped it upside down. So f of x is equal to the negative absolute value. It's being shifted over 1 unit to the right, so that's a minus 1. And then it's being shifted up 3 units. And so that should do it. If we were to plug in numbers, that should be our guy. And so we're just reverse engineering that. So what's about to follow is we're going to give you a kind of a family of functions that we should all be familiar with. The next one is the quadratic function. And so I think you know about x squared. It looks like that parabola. And so the domain is from minus infinity to infinity, and its range is from 0 to infinity as well. And so what we're going to do is just get reinforcement of what we've done on the previous page and do it pretty quickly. We know that this is going to take that parabola and flip it upside down. You don't have to plot points, just draw what you feel is your basic parabola and do the natural shifting. This is a plus 2 being added before we square, and so it's going to move us 2 units to the left, and we're opening up. A minus 3 being done after the fact, so it's the same upwards opening parabola, just shifted down 3 units. This one here is shifted to the right 1 unit and up 4 units to start. That's its regular starting point, what we call a vertex of the parabola, as I'm sure you're familiar with the prerequisites for the course. And we get a nice quick graph like that. They're going to have us evaluate, but you know what 4 squared is. Remember what this is. It's 16. I only wrote it like that for this one right here. Whenever you substitute, you have to do it with parentheses, so we do get positive 49 out of that. And then f of m plus 5. Well, that's going to be m plus 5 squared. We don't want you to leave it like that. We want you to multiply it out. But we're respecting the fact that you've been through a lot of algebra, so that as I write the trinomial without doing the full 4-term expansion, you'll be able to track that. Now, what we're looking at here in D is something that would have come up in an Algebra 2 class because they're trying to prepare us for future classes. But we're being asked to do f of 4 plus h minus f of 4 all over h. And so that's what we do. We do 4 plus h, the quantity squared, plus 4 squared all over h. And we simplify as much as possible. So we know that's 16 plus 8h plus h squared. And I apologize, I have a miscopy here. Remember, it was minus f of 4. And so there is a minus here. I didn't mean to miscopy that. Minus 16 all over h. Well, these 16s at the bookends cancel, so I now have 8h plus h squared all over h. And there's h's in all 3 terms that are present, so I'm going to just pull one out, and we're going to be left with 8 plus h coming out of that. So that's what that guy looks like as a simplified final result. And now they want us to find out, hey, when does x squared equal 9? And so we know what to do there. You could either use the square root property and say, well, that means x is equal to plus or minus the square root of 9, or x is equal to plus or minus 3. Or you could have brought over the 9 and set it equal to 0 and factored. You have lots of, not lots, but you at least have 2 different ways to solve that. So pretty awesome. F of x equals negative 20. When is x squared equal to negative 20? Well, if I use my square root property, right, let me come in here with a different color and put square roots over the top. Remembering to do my plus and minus on the outside there. What I find is that I'm being asked to take the square root of negative 20. Now I know you're familiar with I notation. I don't think they're looking for that here. We're just going to put not a real number, which is a true statement. We could write it in its imaginary form. I don't think they're expecting that of us right now. We will do complex numbers though in this class. If we look at this picture for 4a, we can see that it's a regular parabola shifted down what looks like 1, 2, 3, 4 units. So it's an f of x equals x squared minus 4. Make sure to put that f of x in there, right? So that it's not just x squared minus 4. And then here, what does it look like is happening? We're taking our regular parabola, shifting it down 4 units, but also left 2. So let's talk about that. Left 2 would be a plus 2 before we ever did the square, and down 4 units would be a minus 4. And then an upside down parabola, we know what that's going to do. It's going to have a negative but we are being shifted 1 unit to the right and 5 units up, and that should be our guy. And we're just going to keep doing this with all the other different functions. Hopefully you've seen what all of these look like, but if you haven't, what we're showing you first is the parent graph, for lack of a better way to say that. And so you have this nice little cube graph. And so if I go down this left-hand column, the domain of that is all reals again. You can plug anything in, and actually the range is all reals as well. You can get anything out of that that you want. And so if we take this little snake-like graph and apply the negative, it will flip it. And so what was up is now down, and what is down is now up. Notice that I'm not drawing it like super perfect. That's great. You don't have to put yourself under that stress. The critical point that we're moving is right there in the center. I apologize if you didn't see what I did, so I'll draw an arrow there. That's our critical point, and so we're moving that whenever we need to move. And what we're finding is we need to move it right 2 units, and we're looking the same. We're going up to the right of it and down to the left of it. There's a little flattening out there, which we call an inflection point. You'll search for inflection points when you're in your calculus class. X cubed plus 3, we're going to go up 3 units and do the exact same graph. And negative x cubed minus 1. Ooh, I did something that I did not want to do there. My hand hit the side there. And so when that happened, it sent way down the page. So let me come back right up to where we were, which is right here. Thanks for your patience there. So we have a negative x cubed minus 1. So we know what's going to happen. We're going to be shifted down 1 unit, and it's going to be opening opposite. So it's going to come and be a decreasing function now, but down 1 unit. Pretty cool. Now this will look a lot like the tangent graph, the graph of the tangent function. And all of these shifts, when we go to do the graphing for the trig functions, it's going to look just like this. And so I don't know if we need to keep doing all of this, but I will for at least a little bit. X cubed would be taking 4 and cubing it. That's 4 times 4 times 4, which is 64. And negative 7 cubed is going to be, negative 7 times itself, right? Times itself again. So if you need to, you could pull out a calculator. If you didn't have a calculator, you just sit there and figure it out. Now, remember, it's a negative times a negative times a negative. So when we do negative 7 cubed, it's going to be a negative, and it works out to be 343. M minus 4 cubed, that's m minus 4 times m minus 4 times m minus 4. There's no fancy way around that. So that's m squared minus 8m minus 16. Plus 16, right? Times another m minus 4, and we just got to be careful. Now we just run the m through, m cubed minus 8m squared plus 16m. And we run our minus 4 through, minus 4m squared, plus 32m's, minus 64, right, coming out of there. And so what are we left with? We're left with m cubed. We're used to having the bookends, minus 12m squared, plus 48m's, minus 64. And that would be that guy right there. So when you have f of 2 plus h, well, that's 2 plus h to the third power minus 2 to the third power all over h. It's a very heavy calculus, not heavy calculus, a central calculus idea. That's what I should say. And so, unfortunately, we're going to have to figure out what 2 plus h is. So I'm going to do that off to the side. 2 plus h times itself times itself. So I'm just going to work that off to the side here. So that's 4 plus 4h plus h squared times another 2 plus h, which is 8 plus 8h plus 2h squared plus 4h plus 4h squared plus h cubed. And what do we get out of that? Well, I'll write that over here. We get an 8, and then we get 12 h's, and we get 6h squareds, and we get an h cubed. and that's all sitting over h. And if we hit equals, we realize, oops, I forgot the minus part from this one, minus 8. So that's a translation of this guy right here. So those 8's are going to cancel out, and we'll be left with 12h plus 6h squared plus h cubed all over h. And so that's going to leave me a 12 plus a 6h plus an h cubed. I'm sorry, h squared. I did mean to drop one power there, right? And so that's what we're left with. And so you're just running through each one of those. When does x cubed equal 125? Only for one number, whatever the cubed root of 125 is. And maybe you know that as 5. And how about here where we have the cubed root equal to a negative? No problem. X would be equal to the cubed root of a negative, but cubes can be negative, so this is negative 2. So it doesn't have the same issues that the squareds do. So if you're okay, I'm going to come in here and erase this side work that we did in order to do the problem off on the left-hand side. And then if we go through and look at these graphs, we would see that this is the regular x cubed graph shifted 1 unit to the right, and so it would look like that. This is the x cubed graph, and it hasn't changed. It's going from it's increasing as we look at it, but it has shifted 4 units to the right. I'm sorry, 4 units to the left, 1 unit up. So 4 units to the 4 units to the left, 1 unit up. That's what your f of x is going to look like. And just going to peek up here and make sure I put a minus, and I did. And then right here, what we find is that we're 2 units down. And so we know what this is. This is just f of x is equal to x cubed minus 2. Pretty nice there. It's a mark I made earlier. Some graphs have what we call asymptotes, right? And so this one right here has a vertical and a horizontal asymptote. Let me come in here in red and put, oops, it's already in red. So let me come in green. This y equals 0 line is what we call a vertical asymptote. And the y equals 0 line is a horizontal asymptote. X equals 0 is a vertical asymptote for this one. They're not; those red lines aren't going to cross those. Label the asymptotes on the function's graph. So the asymptotes for this graph are x equals 0 and y equals 0. Those are the two ones. So its domain is not all reals. It's all reals except 0. You will not be able to plug in 0 because you can't divide by 0. Because you can't plug in 0, you're not going to get every element out. You're going to get everything out but 0. That's the range of that guy. And I know you've seen this before. We worked a lot with rational functions in your algebra courses that are a prerequisite for this. This course right here. And so that's your domain and range. If you wanted to stick to interval notation, it would be negative infinity to 0, union 0 to infinity for both of those ones there. But we don't have to plug in points. We know what's going to happen here. We know we're going to invert this graph, right? Looks a little lame, but that's what that guy's going to look like. 1 over x plus 3. Well, we know that this is a shift to the left 3 units. So what's being shifted is that vertical asymptote. That's your key line to go ahead and move. And we still have the same horizontal asymptote because there was no horizontal shifting. There was no shifting up or down. That's a better way for me to have said that. And then we're just going to draw the same graph that we see in the original parent graph with just a new asymptotic line. We know what's going to happen here. It's going to be shifted up 2 units. So what's going to be shifted up? That horizontal asymptote is going to be shifted up 2 units. But the vertical one won't be shifted up. And we're just going to draw that right in here. And then same thing here. We got a couple of shifts, right? Let me go back to the green. I got to move one of my forward 2 units, and down 1 unit. And then it's the same graph, and so it's going to be opening like this and opening like this. Don't worry about the carefulness of the drawing there, just make it a nice rough sketch. The key part is that we can quickly analyze what's going on. And then we have you practice with some problems, and they're teaching us some good algebra skills. Maybe not the first one. If I switch over to a blue pen so we can see it a little bit better, this is just simply 1/4. Remember what this is. This is 1 over negative 1/3, but we know what to do there. We just flip, so this is really negative 3. This is an interesting one. This is 1 over 2 plus h minus 1 over 2 all over h. Now you cannot leave it in this, what they call complex fraction form. And so you've learned a couple of ways to deal with that. One is to clear all the fractions by multiplying through by the common denominator, and the other is to get a solid top and flip and multiply. I'm going to multiply everything by the common denominator of the top, which is, and I'll put it in a different color, 2, oops, it didn't take the different color, 2 times 2 plus h. I'm just going to multiply that through the top and on the bottom. So up top it's got to distribute. And as it distributes to the first one, all I'm left with, the 2 plus h's will cancel and you're left with the 2. You'll remember this when you simplified complex fractions in your previous class. As it goes to the second one, the 2's cancel and you're left with 2 plus h. And on the bottom you're left with h times 2 times 2 plus h. Now I have a huge problem, which many students fall into a trap of. I have to remember that the whole thing is being subtracted. So I got to put that last thing in parentheses, which makes a huge difference. That's why I kept saying huge. Okay, that h is actually negative. And what do you have? Well, your 2's drop out, and so you're left with negative h over h times 2 plus h, and your h's cancel. So in the end, it's really negative 1 all over 2 times 2 plus h. It's up to you whether you want to multiply out the denominator. Nothing's going to simplify, so you can leave it however you want. And then if we solve these equations, when does 1 over x equal 6? Well, you can multiply both sides by x if you were lost, divide by 6, and get 1/6 is equal to x. And when does 1 over x equal negative 7/4? Maybe you do the cross product and you say, hey, 4 is equal to negative 7x. That happens when x is equal to negative 4/7. And you're done, right? So we trust that your old algebra skills and arithmetic skills are there, right? We're going to just be looking at this and saying, hey, what does it seem like the new asymptote is? And it looks like we have a new asymptote up 1 unit. So this is f of x is equal to 1 over x plus 1. This one here looks like it has a new vertical asymptote, and so that would be a shifting 3 units to the right. So this is 1 over x minus 3 is what f of x would be, right? And f of x plus 1. And then, sorry about that, down here we have shifting to the left 2, a shifting of the asymptote down 3. And it seems like it's opening the other way too, right? And did I miss that up here as well? No, so let's remind ourselves what the original function looks like. The original function is opening, well, let me just talk about its concavity. It's concave down on the left and concave up on the right. I might have missed something here, right? And so down on the left, up on the right, we're good there. But up on the left, down on the right. So I am missing something. I'm missing a negative sign on the outside there. This one has the right concavity, so there's no negative sign. And so we have f of x, and we talk about the shifting. It looks like negative 2 is the new vertical asymptote, so it's 1 over x plus 2 on the bottom. And it looks like negative 3 is the new horizontal asymptote, and so we have a negative 3 coming out of there. And then we're going to be doing the same thing with the square root function. I don't know if it's worth your time to have me talk through all of these. Maybe I can skip this one coming through. But each provides their own unique thing. Maybe I can't skip it. I apologize. So you can fast forward it if you don't, if you're like, hey, this is easy. There's some aspects here that I don't want to skip. So notice what its domain is. Its domain, the square root of x, is from it's from 0, and 0 is included, all the way up to infinity. We can't plug any negatives in there because that's the principal square root. And what comes out are things from 0 to infinity. All right, and so what's the negative square root look like? Well, we know what that's going to do. It's going to flip it and go like that. X plus 5, we know what that's going to do. It's going to shift it back 5 units and still look the same. Root x plus 1, we know what that's going to do. It's going to shift it up 1 unit, right? And remember what's happening when we shift it up 1 unit. Our domain is still 0 to infinity, but our new range, because everything's up 1 unit, is now 1 to infinity. Can't ever achieve 0. And then this is the reason why I didn't skip it. The negative on the inside we haven't had an ability to talk about yet. But here what it does, it flips u around the y-axis. Now think about that. This thing has a domain, and its domain is not from 0 to infinity. Its domain is from negative infinity to 0. I have to be plugging in negative numbers so that when I take the negative sign of it, it becomes positive. And so that's its new domain, and so that's why it's looking just like this. But essentially, a negative on the outside will flip you over the x-axis. A negative on the inside will flip you over the y-axis. And then I think you know what the square root of 4 is, and the square root of m minus 4 would just stay just like that, right? So this is 2. Maybe we should show you this. This is h over the square root of 9 plus h minus the square root of 9. Now we cannot leave it like that. And it's not just because the square root of 9 is known to be 3. You know that you cannot have a square root on the bottom, so we have to rationalize the denominator. How do we rationalize the denominator when there's a binomial on the bottom? The conjugate. Now keep in mind, you've been through 2 classes that have talked about the conjugate. They are not going to talk about it again, but that's why we're bringing these things up. You're going to have to use it. But that's the way your future classes are going to be. They're going to assume that all the algebra is old hat, that you can do that. And so if you remember, the conjugate is the exact same terms with the opposite sign in the middle. So up top we have h times, and I'm not going to even multiply it through, 9 plus h plus 3 times those 2 terms. And on the bottom we have root 9 plus h times itself. Well, that's 9 plus h. We know that the middle terms will cancel out, so I'm not even going to write them. And then negative 3 times positive 3 is minus 9. These 9's are canceling out, and therefore the h is canceling out, which leaves us with root 9 plus h plus 3. That's what that guy is. And if we come down here, square root of 6 is the square root of 6. Nothing you can do there. Square root of negative 8 is undefined, right? Or not a real number. It's not even part of the domain. That's why it's not working. You know the domain's from 0 to infinity. When does the square root of x plus 3 equal 5? Hopefully you remember how to solve square root equations. You square both sides, and you did ones way harder than this, and then you solved. 22 coming out of that. I hope I'm not making any arithmetic mistakes along the way. I'm just trying to show you what we do in class. Skipping maybe a lot of these, but not skipping, but just kind of going quickly through because we could get the verbal output out. I hope you recognize this as the regular square root graph shifted down 2 units. And this is the regular square root graph shifted to the right 1 unit. And flipped over. Apologize. It is flipped over, so there's a negative after the fact. And this is the regular square root graph. Looks like it has been shifted to the right 2. I don't need those parentheses in there. Let me erase them in case that adds confusion. And then what else is it doing? It's being shifted up 1 unit. And so that plus 1 is outside of that square root. Okay. And then the last thing, right, because we're going through page 13, is circles. And so circles are going to be pretty important for us in trigonometry, because trigonometry is a circular function. And so we want to remind you that there's a general form to a circle. And so x squared plus y squared equals 16 is the general form. And the general form looks like this: x minus h squared plus y minus k squared is equal to r squared. And so the center, when it's in this form, would be at hk, and its radius would be r. Right? So that's my r. Sorry if that looks like some kind of weird v. But we'll learn notation together. So if I look at number 1 doesn't have anything being added or subtracted to the x or the y before you square it. And so the center is at 0, 0. And the radius is not 16. Remember, it's equal to r squared. The radius is 4. Here in number 2, the center is 0, 0. And what's the radius? Root 10. If I go to number 3, the center is at 3, 2. And the radius is at 2. So hopefully in your intermediate algebra class you took the time to do some conic sections. It's possible that you didn't, but this is one of the conic sections, and so was the parabola that we did earlier. If we look at 4, it's x plus 4, so we're going negative 4 in the x direction, 5 in the y direction, right? And the radius is 1, because the square root of 1 is 1. The center for number 5, nothing's being added or subtracted from the x. 3 is being added to the y, so that's a negative 3 in terms of the center point, y direction. And root 7 would be the radius. Here, be careful. If we look at this too quickly, we won't realize that the y is written first. So there's a 0 in the y coordinate of the center point and a 2 in the x coordinate, because x minus 2. Remember, if it was x minus h, the center was at hk, right? And so it's 2, 0, and the radius is 3. And then here, we want to remind you that you know how to complete the square. So we really can't read the center right now until we complete the square. And that's going to be x plus 5 squared plus y minus 3 squared is equal to 20. So my center is at negative 5, 3. And my radius is the square root of 20, but don't leave it like that. You know that that reduces to 2 root 5, right? Because 20 is 4 times 5. Square root of 4 is 2, root 5 coming out of there. And then lastly, that's number 7 didn't necessarily have us complete this square, but this one will. What we're going to do is kind of rewrite this guy with some spaces in there. So hopefully you learned how to complete the square. If you didn't in previous algebra classes, you should write your teacher and be like, what'd you do to me? So if you remember completing the square, we have to add something to this. So we're isolating the x's and we're isolating the y's. And we need to add something in there. I need to add something that's going to make it a perfect square. And what does that is half of the middle coefficient squared. So half of negative 8 squared. Half of negative 8 is negative 4, squared is 16. And if I added it to the right-hand side, I got to add it, add it to the left-hand side, I got to add it to the right. And then I got to take half of 2 and square it, which is 1. And we come up with this very nicely. X minus 4 squared plus y plus 1 squared is equal to 14. And so our center is at 4 common negative 1, and our radius is root 14. Root 14 won't simplify because it's made up of just a single 2 and a single 7. So that's the first video that I've done for you here, and expect others along the way that follow this supplemental packet that will help you with the work that you do.